Okay, now we're going to do fluids part 3. And we're talking about pneumatic power, so we're talking about gases. When we talked about hydraulics, we talked about how liquids are like solids because they don't compress very much. Whereas gases, we can compress them a lot and they'll change volume a lot, so they act more like a spring. Some early uses of pneumatics were, for instance, bellows, to get more air into fires to raise the temperature for people working with fire. This is an interesting experiment that was done by this guy, where he took 2 spheres and got a vacuum inside of there by sucking the air out. Then it was just being held together just by the atmospheric pressure. Nothing else was holding it together. And literally he hooked up teams of horses to both sides, and it was so strong that they couldn't pull it apart. Also, the first subway from 1870 was powered by pneumatics. You'll notice the subway wasn't very long, but at that point in history, pneumatics was completely new. Most of what we use with pneumatics today is based on these early uses. The 3 important properties when we're talking about gases are temperature, pressure, and volume. And you probably have already learned some of this in chemistry and in physics. Gases have no definite volume. They take the volume of whatever container they're in. We can compress them a lot, and they're very light. One of the important things to catch is that we want to talk about absolute pressure when we're using our formulas. Gauge pressure means if I have a little dial that measures the pressure inside of some container, it'll tell us gauge pressure. That's what the dial reads. But absolute pressure is what we really need, which is atmospheric pressure plus gauge pressure. You'll want to write this formula down. We're going to have to use this conversion in our problems that we're going to work. And what you need to remember is that atmospheric pressure is 14.7 pounds per inch squared. So if you have a gauge that reads 120 pounds per square inch, and you want to find absolute pressure, you just add your gauge plus atmospheric to get your final absolute pressure. The same thing is kind of true for absolute temperature. In science, you're probably used to dealing with Celsius and Kelvin. When we're using English or customary units, we talk about Fahrenheit, and instead of Kelvin, we talk about Rankine. In Fahrenheit, absolute zero is negative 460. So Rankine, to find the Rankine, you just take Fahrenheit plus 460. You do need to write this formula down. For instance, if we have something that's 65 degrees Fahrenheit, what's its temperature, absolute temperature in Rankines? You just take the 65 plus 460 to get our answer in Rankines. The perfect gas laws, again, you may have seen these in science already, are these 3, and we're going to go over what each of these is. The first one is Boyle's law, where we're talking about volume and pressure. And these are inversely related. As the pressure goes up, the volume goes down. Here we're holding the temperature steady. The temperature's not changing. So it's just P times V initially is equal to P times V in the final, where V is volume. So here's a problem and what it might look like. A cylinder is filled with this volume at this pressure, and then we compress it to a smaller volume, so it's the final pressure. Well, it's important to lay out what your variables are. Be sure you keep track of what your initial numbers are versus what your final numbers are. If you switch them, it's going to be wrong. First, our pressures have to always be converted over to absolute. So we take this one, add the 14.7 that we learned on the previous slides to get our absolute pressure for 1. Now we can plug them in the formula. We're just straight plugging these numbers in from up here and solve for P2. However, remember this is the absolute pressure at the end, not the gauge pressure at the end. Charles's law does volume and temperature. These are proportional. As the temperature goes up, the volume does too. Here's our formula. You want to write this down. Do notice that the temperatures have to be an absolute. So we have a problem again, and we're again talking about initial and final. Here's our initial volume and initial temperature, and our final temperature. You need to be careful that you write these numbers down carefully, keeping track of which is initial and which is final. You do have to convert them over to absolute temperatures. Once you've done that, you're ready to plug them in your formula. We're literally again plugging in volume and our absolute temperatures into the formula and solving for the missing variable. Our last one is Guy-Lussac, and it talks about pressure and temperature. Do notice that both of these have to be changed over to absolute, and they're inverse again. As the pressure goes up, temperature goes down. So here's an example of the formula. Initial volume, and it's a sealed air tank. So a sealed tank is not going to change in volume. But in the morning, the temperature is lower than it is in the afternoon. This is our gauge pressure in the morning, and we want to know the absolute pressure in the afternoon. So we carefully write down our variables from our problem, keeping track of which ones are initial and which ones are final. And then we convert over to absolute pressure. We also need to convert over to absolute temperature. If you don't convert to the absolutes, you won't get the right answers. Now we plug them into our Guy-Lussac's formula and literally solve for the missing variable. Remember, this is absolute. If they wanted gauge pressure, we'd have to go back and subtract. And that's what they're doing here. What would be the gauge pressure? Well, we need to go back and subtract off the atmospheric pressure to get the gauge pressure. And that's the end.